All right, here we are on Chapter 1, Lesson 2, starting our second week of focus note-taking. What is Earth's structure? Building background. Earth has a layered structure. At the surface is a layer of solid rock called the crust. Below is the mantle, made of softened rock. Below the mantle is Earth's core, a very dense layer made mainly of iron. By studying Earth's structure, scientists can predict how the surface will change. Okay, so you can actually see the layering effect in this picture. And everything that we live on is the crust. I don't think we ever actually even see the mantle. It is so deep. Okay, we start on page 18, and we're going to set up our focus note-taking structure. So, first thing's the same. I write my name, Mr. Rob. Don't put Mr. Rob. That's my name. You put your name. Class or period. AVID, capital A, capital V, capital I, capital D, 6. Date. Today is September 9th, I believe. So 9/9/2020. Okay. Topic or objective. We're going to put Chapter 1, Lesson 2. Oh, you know what? Let's say this first. Science, capital SCIENC. F, capital N, capital T. Science FNT. Chapter is going to be abbreviated capital CHP, and then the number 1. Lesson goes like this, capital LES, number 1. And it is called Earth's structure. So Earth's, capital EARTH', structure, capital STRUCTURE. Okay. Now that is going to be the same thing as our blue title, like we did last time. So I'm getting my blue pen, and I'm writing down the title. Oh, I know something I forgot to do. I have to fold my paper in half. So take your paper, line it up about halfway, fold it in half all the way down, and now you have that nice little visual. Okay, over here in the red, but make sure you're not in the part that's going to get torn off when you tear your paper off. Let's do the title. Earth's, capital EARTH', structure, capital STRUCTURE. It's okay if it bleeds over a little bit into this column, but you definitely don't want it to go too far to the left where it's going to get torn off. Okay, let's write main idea, capital MAIN, idea, capital IDEA, slash essential, capital ESSENTIAL, question, capital QUESTION, and we're going to put parentheses, capital E, capital Q. From now on, we're just going to call the essential question our EQ. Okay, just like last time, we're going to do it note style where it's not complete sentences. Earth is made up of different layers. Each layer has its own unique characteristics. Characteristics like what information there is about it, what materials it's made out of, how thick or how deep it goes in the earth, those kind of things. So, let's say here, main idea, essential question, Earth, capital EARTH. Notice I have switched back to my pencil. Has, HAS, different, DIFFERENT, layers, LAYERS, period. Each, capital EACH, is, IS, unique, UNIQUE, period. So each layer is unique. All right, looking back to what we did last year, last week, the very first thing we did was our vocabulary words. So using your pencil, let's come over here and look. Asthenosphere, that's a TH, so it's asthenosphere. Core. Lithosphere, that's a TH with your tongue. Lithosphere. Mantle. Yes, these are a little tricky to say, but that's what our vocabulary words are this week. Okay, asthenosphere is on page 20. Oh, look at all those vocabulary words. Okay, let's find it. There it is. Nope, there it is. and go backwards until you find the start of a sentence. The plastic part of the mantle beneath the lithosphere is called the asthenosphere. Now, when they say plastic, they don't mean it's literally made out of plastic material like this pencil sharpener. They mean plastic like it's a little bit softer. It's not hard like rock. It's more like plastic where it can bend and break or twist and those kind of things. So let's go ahead and put that. Let's see. A-S-T-H-E-N-O, asthenosphere, S-P-H-E-R-E. It's part of the mantle, and it's beneath the lithosphere. So, part, P-A-R-T, of, O-F, mantle, M-A-N-T-L-E, comma, below, B-E-L-O-W, lithosphere, L-I-T-H-O-S-P-H-E-R-E, lithosphere. Okay, that's the first one. Let's keep going in the order that they show us. Core, okay? Core, and then we go backwards to find the start of a sentence. The innermost of Earth's layers is the core, which extends to the center of the Earth. So, innermost layer, center of Earth. Following that line right over here, core, C-O-R-E, innermost, I-N-N-E-R-M-O-S-T, layer, L-A-Y-E-R, and then what did we say? Extends to center. Center, C-E-N-T-E-R, of Earth, capital E-A-R-T-H. So the core is the innermost layer, and it is basically the center of the Earth. Okay, the next word is going to be lithosphere. L-I-T-H-O, litho, sphere, S-P-H-E-R-E. Remember that word sphere is a sphere or a ball, right? A circle. Like a peach is kind of sphere-shaped. The Earth is kind of sphere-shaped. Basketball, a volleyball, a soccer ball are all sphere-shaped. So they're telling us that these are all part of the Earth's sphere shape. Lithosphere. Find the word. Go backwards to the start of a sentence. This rigid upper mantle and crust combine to form a rigid shell called the lithosphere. So the lithosphere is a combination of the crust and upper mantle. Okay? So lithosphere is a combination of upper, U-P-P-E-R, upper mantle, M-A-N-T-L-E, and, so we're going to say plus, the crust, C-R-U-S-T. The lithosphere is a combination of the upper mantle and the crust. And it says that it's rigid, so let's go ahead and write that. Equals rigid. Rigid means hard and not very bendable, right? Okay. Any other vocabulary words? Mantle. Yes, mantle. There's mantle. Going backwards, the solid layer just below Earth's crust is the mantle. Mantle, M-A-N-T-L-E. Solid layer, S-O-L-I-D. Layer, L-A-Y-E-R. Below, B-E-L-O-W. Crust, C-R-U-S-T. Now, it's a lot of words, and it's kind of hard in our minds to visualize where are all these things at. Fret not, because in page 21, when we start taking notes, they have this drawing, so we will draw a sketch that's very similar to that. Okay, let's think about how many days we have and how many pages we have to get through. So we have Wednesday, Thursday, and Friday this week. Only 3 days because it's short. We have 1 set of pages, 2 sets of pages, and 3 sets of pages. Well, look at that. The shortest week has the shortest chapter. Aren't we lucky? Huh. I never noticed that before. All right. Go ahead and get your red pen, and we're going to write this title, Hot Inside. So let's come over here. Let's skip a line just for some visual space. Capital H, hot inside, capital INSIDE. Okay, switch back to my pencil. In many parts of the world, columns of steaming hot water can be found shooting up through Earth's surface. These boiling fountains are known as geysers. Geysers form where water drains down a deep channel in Earth's surface. Okay, back to this. This helps you pronounce the words if you don't know how. Guy, like, hey, look at that guy over there. Zers. At the bottom of the channel, hot rocks heat the water, forming steam that pushes water to the surface. Finally, the built-up pressure forces the remaining water to erupt in a sudden explosion. The existence of geysers suggests that Earth is hot inside. Okay, so summing up this whole little paragraph, it's about geysers telling us that the Earth is hot inside. So over here in hot inside, geysers, Geysers, arrow, hot, HOT, inside, INSID. So geysers help us know that the Earth is hot inside. Let's try to draw a little picture based on this description so we can see what we're talking about. There is a picture of a geyser, and I bet you're already thinking, oh, that kind of looks like a volcano. And then these are hot springs, which are very similar to a geyser. That water is actually boiling hot on the surface of the Earth because the magma and lava underneath is so close, it heats it up. Okay, so let's see. What do we have here? Hot water shooting up through the surface. Water drains into a deep channel. Hot rocks heat it and form steam that pushes out. The built-up pressure erupts. Okay, so let's go ahead and draw something that is a little bit like a volcano. Let's put heat down here. H-E-A-T. Heat. Exclamation point, because there's so much heat. Let's capitalize it. Capital H. Heat. Okay. Water, right above that. Water. And then let's draw like some little steam things coming out. Steam, S-T-E-A-M. Eruption, E-R-U-P-T-I-O-N. So all this heat down here heats up the water so much it turns to steam and erupts out the top of the surface. Right? And down here the heat is deep underground. So under, U-N-D-E-R, ground, G-R-O-U-N-D. And then the steam eruption happens at the surface, S-U-R-F-A-C-E. So it's like a volcano, but instead of lava or magma erupting, it's just hot water steam. Still very hot, still dangerous if you were to touch it, but a slightly different mechanism. Okay, let's keep going. Yellowstone National Park in Wyoming is well known for its numerous geysers and hot springs. Long before this region became a tourist attraction, Jim Bridger explored its wonders. That's this guy right here. He lived, let's see, about 100 years ago. No, I'm sorry, 200 years ago. Wow. Bridger was a fur trader, scout, and mountain man. He told everyone he met about the many geysers and amazing sights of the region. Okay, so what's super important here? Yellowstone National Park, geysers and hot springs, and Jim Bridger. Okay. Yellowstone, capital Y-E-L-L-O-W-S-T-O-N-E. National, capital N-A-T-I-O-N-A-L. Park, capital P-A-R-K. Many, M-A-N-Y. Geysers, G-E-Y-S-E-R-S. Many geysers slash, what did they call them? Hot springs, H-O-T-S-P-R-I-N-G-S, hot springs, two different words. So hot springs are kind of like a little pond of water, but they're boiling hot a lot of the time. There are some places in the world where they're just hot enough to feel good, like a warm shower or a spa, but a lot of places they're boiling hot, like you could put food in them and cook it. You wouldn't eat it because of the nasty chemicals in the water, but it's that hot. Okay. Visit Yellowstone today, and you too can see evidence of Earth's hot interior. But just how hot is it inside? Good question. Okay, geysers spout up 70 feet with a terrible hissing noise at regular intervals. In this section are the great springs, so hot that meat is readily cooked in them. So he wrote journals to tell everyone what it was like there. So let's go ahead and put his name, Jim Bridger, capital J-I-M, Bridger, capital B-R-I-D-G-E-R, and let's say something like Aero Explored, E-X-P-L-O-R-E-D. So Jim Bridger explored the hot springs and the geysers at Yellowstone National Park. Okay, that's it for everything for pictures and captions. Let's move on to the second page. By studying mines and holes drilled in the crust, scientists know that the temperature increases about 2 to 3 degrees Celsius for every 100 meters, which is about 300 feet. That's about the size of a football field. So if you dig down into the earth the length of a football field, it starts to get a little bit hotter by 2 or 3 degrees Celsius, which is actually a little bit more in Fahrenheit. However, the deepest drill holes reach less than 15 kilometers, or 9 miles below the surface. So scientists depend on indirect evidence, such as geysers and volcanic activity, to learn what Earth is like inside. Basically what they're saying is, even though 9 miles sounds like a long way, that is not very deep into the crust, and that's not even getting down into the mantle, the asthenosphere, the lithosphere, the core, all those other fancy terms. So we're barely scratching the surface of the Earth. That means we have to rely on indirect evidence or other pieces of information that kind of help us guess or make an inference. So we can't really dig far enough down to see the lava or magma for ourselves, but we can tell because of these geysers, and we can tell from volcanoes there must be something hot underneath the surface of the Earth, forcing all that lava and magma up, or heating up all that water and turning it into steam. So indirect kind of means that you don't actually see it, but you can make an inference from a lot of other information. They also conduct experiments on surface rocks and minerals under conditions of high pressure and temperature. Okay, so the important thing here is temperature increases as you move down, right? So temperature, T-E-M-P-E-R-A-T-U-R-E, goes up, arrow up, as your depth, or D-E-P-T-H, goes down. So, as your depth increases, or you keep getting further down into the Earth, the temperature starts to increase too. Okay, now what else? Indirect evidence, right? I-N-D-I-R-E-C-T, evidence, E-V-I-D-E-N-C-E. That's basically like saying, make an inference. I-N-F-E-R-E-N-C-E. Use all the other information you have to make a really good educated guess. But then run experiments to test your ideas and see if they're true. So experiments on rocks and minerals, high pressure and temperature. So experiments, E-X-P-E-R-I-M-E-N-T-S. Experiments, pressure, P-R-E-S-S-U-R-E, / temperature, T-E-M-P. And we're just going to leave it there at temp for temperature. So Jim Bridger explored the many geysers and hot springs at Yellowstone National Park. People and scientists have learned that the temperature increases as you go further down, deeper into the Earth's center or core. We use indirect evidence to make inferences, but we also run experiments using pressure and temperature to find out what's going on with rocks and minerals. Okay, let's come back here. Scientists have found that much of Earth's internal heat comes from energy released when radioactive elements such as potassium, uranium, and thorium break down. Some heat is left over from Earth's formation. Okay, so a lot of our heat comes from radioactive elements breaking down. Okay, heat, H-E-A-T, from, F-R-O-M, radioactive, R-A-D-I-O-A-C-T-I-V-E, from radioactive breakdown. We're going to indent to make some space, B-R-E-A-K-D-O-W-N. And apparently it's somebody's birthday over there, so I'll pause this just a second. So radioactive breakdown is basically just when these elements are not very stable. They can break into smaller elements, and they release a little bit of energy when they do that. But there are so many elements in the center of the Earth doing that, that it's enough energy to heat up the core and to heat up all these geysers and volcanoes. Okay. Also, there's heat left over from Earth's formation, so heat from radioactive breakdown, and downline, the number 3 downline, that's the and symbol, heat from radioactive breakdown and Earth, capital EARTH, make it really tiny so it fits, formation, FORM, notice how I'm squeezing it all together, ATION, from Earth formation. Okay, we're almost done. More information about Earth's interior can be gained by observing seismic waves. These waves are vibrations that travel through the solid Earth during earthquakes. Seismic waves change as they move through different kinds of materials at different temperatures. Okay, so that whole little thing is about getting information from seismic waves. Okay? So, seismic, S-E-I-S-M-I-C, waves, W-A-V-E-S, and they travel through the solid Earth. They change as they move through different kinds of materials at different temperatures. Okay, so seismic waves change, C-H-A-N-G-E. What do they depend on? Seismic waves change. It could be either the material, M-A-T-E-R-I-A-L, material, / temperature, they said, T-E-M-P-E-R-A-T-U-R-E. So seismic waves change depending on the material they're going through or the temperature of that material. If you think of like the ocean and the waves that you see, or if you're sitting in a pool and you're kind of bobbing up and down as somebody is causing and making waves in the pool, seismic waves are a little bit similar to that, but they are traveling through the layers of the Earth, through the dirt, through the rock, and through the crust. And you can tell from the seismic waves what kind of material it's going through or the temperature of that material. So remember, we're doing experiments. If the seismic waves are moving really slow, that might tell you something about the material. Maybe it would be softer, kind of like the foam on a bed. But if it's moving really, really fast, maybe that would be a harder material, like a hard rock or a layer of clay and hard dirt. Okay, let's look at our pictures. Yellowstone National Park's hot springs, geysers, and mud pots are evidence of Earth's hot interior. Do we have something like that? Yes, we use indirect evidence to make an inference, and that was talking about the geysers and hot springs. Earth's temperature increases about 25 degrees Celsius per kilometer in the crust, then more slowly from the upper mantle to its center. So what this little graph is trying to tell us is, as you get deeper and deeper and deeper and deeper and deeper into the Earth's core, the temperature gets hotter and hotter and hotter and hotter. And we're talking about thousands of degrees Celsius. That is hot enough to melt metal, right? This is not just warm compared to us. Thousands of degrees Celsius is melting metal. And that's why they think that the inner core of the Earth, being made of iron, is molten or liquid iron. Okay, do we have something about that information? I think we do. Yeah, the temperature increases as we go further down, or the depth increases. As we get deeper and deeper into the Earth, our temperature goes up. Okay. Last thing to look at, the compare and contrast. How does Earth's temperature change with depth below the surface? Can we answer that question? Yes, we can. The Earth's temperature changes with depth below the surface by increasing. We know that the temperature increases as you get deeper in towards the core. We know this because we have indirect evidence and can make an inference. For example, there's a lot of heat from radioactive breakdown that is causing geysers and hot springs in places like Yellowstone National Park. So you see how they ask us questions, and we are able to answer those questions using our notes. And we're able to turn it into complete sentences even though our notes are not complete sentences. Okay, that was a long one, but the first day is always long because it always takes time to set up the main idea, essential question, the topic, all of the vocabulary words, and then get things started. All right, good job. Roar Wildcats.